Is this a yes? Right. We can start, and if you guys have any questions, can you please ask me? Right. Well, I'm going to start the process, waiting for other people, hopefully, to join us. If not, what can we do? Right. One thing that I think you should know.
Recording in progress.
Last time, when we did the last week the tutorial, one of the things I had to deal with was the so-called the kernel. And we came up with Stokes' theorem that says that when you take the kernel of E over a surface, we said this is going to be equal to the field itself times dl. And then one way to check that the field is conservative is that if the kernel of that field is going to be equal to 0. Now, that can be said equivalently that this closed integral, line integral of E dl is also equal to 0. So you can use those theorems of advanced calculus or vector calculus to your advantage a lot of times to calculate some expressions that otherwise they might pose some challenge. Right. So this is the case again of the kernel of E, and Stokes' theorem tells us that the surface integral of the kernel of E over a closed surface is going to be equal to the line integral of that field itself over dl, so it's a line integral. And one way to check that a specific field is conservative if, in essence, the kernel of that particular field is equal to 0, or the line integral, a closed integral, in other words, the beginning point, the starting point, and the ending point is the same exact point, so that has to be equal to 0. So different ways I want to say the same thing, but sometimes one formula is probably preferable in order to calculate something with respect to another. Right. So let's move a little bit forward. And if we look at the tutorial, the first question, in the one that refers about capacitance and dielectrics. So we have a parallel plate capacitor, and we're looking about the distance between those two plates when certain conditions are actually valid. So there is the charge, and in that particular case, when one plate is charged positively, the other one is charged negatively. So the charge is given to us, it has a specific value that is available, it's in our disposal. When we have a parallel cell capacitors, the electric field that is between them is given by this expression over here. In other words, the electric field intensity is the sigma, where sigma is the density of the charge in either the positive or the negative plate of the capacitor divided by the permittivity. And obviously it has also a direction, and the direction obviously depends on which plate of the capacitor is the positive one and which is the negative. Usually the electric field lines they go from the positive to the negative. Yeah. So E in essence, for any intended purpose, is going to be equal to sigma over epsilon. Sigma is the density of the electric charge, epsilon is the permittivity, I think in this particular case, it's safe to assume that that's a free space. So it's the non-permittivity of free space. Sometimes it would put like epsilon 0. And then, of course, it has also direction. The direction goes from the positive to the negative. As if we assume in this case, for instance, the whole thing is oriented upwards, then we have to put a minus sign over here to indicate again that the electric field goes from the positive plate of the capacitor being the upper part of the upper plate of the capacitor towards the lower part. Right. Okay. So if somehow we take this expression for the as the line integral of the electric field along the line, along the path that is somehow it is being characterized by this expression over here. So this is going to be again, every time you see that electric field is equal to the gradient of a scalar field, that's a very strong indicator that this field is basically conservative. And if it's conservative, it doesn't matter, that's by definition, it doesn't matter what is the path we're following. It's going to be always the same. In other words, if I have somehow one point over here that is below the field, I have another point B over here, then the work done by moving a positive unit of charge from this point to the point A to the point B, no matter what path we follow, it's always going to be the same. That's the whole definition of a conservative field. So this is basically going to be E, which we found before is sigma over epsilon, and then also has a direction. But this is you take it the same exact direction, in other words, the same exact unit vector along this thing over here. Now, when the unit vectors are the same, and it's of unit magnitude, then the inner product is equal to 1. So this will thing over here, given that sigma and epsilon, in other words, the density of the charge and the electric permittivity constantly come outside, so sigma over epsilon. And then when we take the integral dl, yeah, in the case of two capacitors that separate by a distance, let's say w between them, this integral in S will give us w. So this is basically sigma over epsilon times w. Any questions here? No questions, right. Now, if we do the same thing with the potential, we call the potential phi. So if we take the gradient for the potential and just rewrite it just for convenience. So this is basically partial of phi with respect to x times I, partial of phi with respect to y times j, plus the partial of phi with respect to z times k. Keep in mind, this is only true for Cartesian stellar coordinates. You go to the polar coordinates or cylindrical coordinates, or you go to spherical coordinates, the expression here will be different. And most of the times it's much more complicated, especially for spherical coordinates. Anyhow, so if we do the same thing, exact thing, so if we take this from 0 to d or w, whatever you want to say, the distance of the gradient of phi times dl, this again by definition, because we take dl, let's say, is in the z direction, so now we're going to have only the z component. So the x and dependence on the x and the y component is irrelevant, and we'll basically ignore it. So this gives us by fundamental theorem of algebra minus phi of w minus phi of 0, which is basically delta phi. And based on the definition of our problems, this is the 5 volts, right? So this is a given quantity. And obviously we have everything else we need in order to be able somehow to find what is this distance. Yeah? Right, so this is pretty much is that something else? Don't remember. Does anybody remember if, or can check to see if this problem is asking for something else to calculate besides the distance between the two plates? Right. So hopefully the concept of the potential In other words, the difference in terms of voltage between 2 points and its relationship to the electric field is understood. In essence, we go from one to another by taking either the electric field and then we integrate it over the line, and it's going to be equal to take this expression, that should be basically equal to phi, right? Or otherwise, and what here have specified what is the beginning and the end of this line integral. So this is going to be basically phi of alpha minus phi of beta. Another way to express this relationship is that the gradient of phi or minus gradient of phi equals basically with phi, and again this is consistent because the gradient of phi is a scalar quantity, a function of x, y, z, or if it's linear coordinates of r, theta, and z. And E also has, it's a vector has 3 components, so it's an equation between 2 vectors. Right. Let's move to the next problem, which is pretty much along the same lines. Can someone tell me whether or not you cover those things in the theory? Someone please tell me whether or not you cover those things during the theory.
I think some of them.
Some of them, right?
Yeah.
It's something that I need to emphasize or elucidate so you can actually understand it better. Well, anyhow, let's see this problem, and again, in the process of solving the problem, if we encounter any sort of unknown or difficult, we'll actually discuss it.
Okay.
Right. I think the problem, this is the second problem, if I'm not mistaken, in the tutorial that talks about the potentials of capacitors. So that's pretty much maybe the topic you covered yesterday during the lectures. Yesterday in the lectures, there are 2 hours. 1 hour was about capacitors, the other hour was about transmission lines or something different.
Yes, capacitors and transmission lines.
It was about transmission lines. Now, keep in mind that transmission lines will not be in your exam, but you are given the lectures for completeness so you can have some sort of exposure to transmission lines, at least to understand in general what it's about. Okay, let's move now to the tutorial. So we do have a charged sphere, and what we're looking for is, we're looking about the potential, the different distances from the center of the sphere. So we have a sphere that has a certain radius, we call it capital R, and we try to figure out what is the potential of that sphere at points that is inside the sphere, in other words, in the interior part of the sphere, and the points that at the exterior part of the sphere. Yeah?
Yeah.
Now, the first thing we need to do is we need to figure out how do we find what is the intensity of the electric field, both inside and outside. Okay, let's do it again independently, and then we'll come over here where I have all the formulas written, so you don't have some out of truth time. All right, so I'm going to erase these things here, and we're going to solve this problem. Okay. So what we have is we have a sphere that has a radius equal to r. The first question to ask is that what is the electric field intensity inside the sphere? With this angle, with this, the distance from the center of the sphere equals small r. Any suggestions on how we can actually solve this problem? When it comes to electrostatics, the first thing that comes in mind is should be
Electric field.
I'm sorry? Yeah, please say it again.
Is it the field?
Yes, the field. Then what is the name of the law that we can apply?
Is it Gauss's?
Very nice. So we take Gaussian law. So this is basically the dot product, the inner product of the electric field intensity, which is E times ds. Now ds is itself a vector. It has a direction which usually people like somehow to put it n to indicate the normal. That's why they use the word the letter n. The normal to the surface, and again, obviously has a magnitude as well. So it's basically, well, you see it a lot of times written this way. Now, E itself again can be written as something that has a magnitude and also a direction. And the same comments we did before about unit vectors, when they are the same and multiplied together, the result is basically equal to 1. So now the expression we had that was vectorial, now it becomes just the multiplication of two quantities that they are scalars. If we take an homocentric sphere that has the center at the center of the sphere that we're dealing with a radius small r, at every point along this surface, the value of E is constant. If it's constant, it can actually come outside of the integral. So E can come outside, and now we have the area of a sphere. Does anybody can tell me what is the area of a sphere? Can someone please tell me what is the area of the sphere?
4 pi over 3.
1 pi r squared, yeah?
Yeah.
That's the area of a sphere. Actually, sorry, this is small r. And this obviously has to be equal to Q. I can put the epsilon over there, or I can put the epsilon here. Let's put it over here. So Q enclosed, in other words, the enclosed quantity inside that sphere. Can someone tell me how we can calculate this enclosed quantity inside the sphere? Now this is the sphere we're talking about. Yeah. We took a sphere that it's homocentric, in other words, it has the same exact center as the one that we're dealing initially. And we're now trying to find now at any point in that sphere, in the surface, what is the value for the electric field intensity. We said because of symmetry, it is equal everywhere, so it can come outside of the integral. And then hopefully we know that the surface area of a sphere is 4 pi r squared. We can prove that, but we'll leave it for the moment. If you want, I can at a certain point, I can actually prove it to you. If that's the case, again, Q, it should be the density, the charge density, and then the volume of that sphere. And the volume of the sphere is 4/3 pi r cubed, right? And then epsilon, it should be over there. So from here, I can solve for E. And E in that respect is again, the 4 pi and 4 pi, they will cancel. So sigma r 3 epsilon 0. Which is pretty much reminiscent of what we've done before. Yeah?
Yeah.
So, what I've done over here, so the 4 pi, this was 4 pi r squared. And this was this. So from here, we can actually solve for E, and E was this thing over here, right? Okay. And of course, if we want somehow to express it in terms of a vector quantity, we can actually put also a unit vector that can be K, can be R. It's up to you to decide. As far as, again, if you're consistent and you can specify what is the direction of that thing, you're perfectly fine. But the magnitude is, again, sigma R over 3 epsilon 0, right?
Yeah.
Right, okay. Well, we're going to do the same exact thing for the sphere, which is outside of, so in other words, we take somehow as our reference, or the point, the distance from the center of the sphere. We want somehow to calculate what is the electric field intensity. A sphere which is outside of the sphere which has the charge. Okay. So let me see if I have those things over here. So the first one, well, it's a mess over here. Right. I think, okay, so this is the one we just found, yeah?
Yeah.
So E of R, when the R is smaller than the radius of the sphere with the charge, is going to give you by this expression. That's the one we just proved, yeah? Good. Now, please tell me now how you can find, so this is the sphere that has the charge. This distance over here is R. How do I find what is the electric field intensity in the distance R? Well, now R is bigger than R. So the small r is bigger than the capital R. How do we find, again, the electric field intensity? We do the same exact thing as before, yes?
Yeah.
Which is basically Gauss law, the integral ds. And initially we start as being vector quantities, and again, for the same exact reason we expressed before, then they can be expressed as algebraic quantities or scalar quantities. The E again is constantly come outside, so it's basically E and then 2 pi R squared. And this is going to be equal to whatever is the Q enclosed divided by the permittivity of the space. Right. Now let's see what is the Q enclosed. The Q enclosed is basically the integral of sigma dV. Yes, and then here this divided by the permittivity of the free space. Now, sigma dV, assuming that sigma is a uniformly charged, can also come outside. Can someone please tell me what is the volume of a sphere?
Over 3 pi R cube.
4 pi over 3, yeah?
Yeah.
And then?
R cube.
R cube, very nice. And this also is divided by epsilon. So what I need to do then is, again, take this expression over here and equate it with this expression over there. If I do that, then I can find that epsilon in this particular case is going to be equal to sigma 4 pi 4, actually, I'm going to have 2 somewhere there. I made a mistake again. This is not 2 4 pi r, it's 4, yeah? You remember that? The surface of a sphere is 4 pi r squared. So again,
Yeah, area. Mm.
this is not there. So 4 pi and 4 pi will cancel each other. We have r to the power of 3 over 3 epsilon 0. I hope that's correct. Let's check it. Right, so for r is greater than, you see that here, for r, is that what we found before? I hope so. Can anybody verify that this is what we found? So when r small is smaller than capital R, that's the expression for the E, and when r is bigger than capital R, that's the expression for E. What's the name for E? How do we call it?
Epsilon.
What is the name for E? What's the physical quantity that we name E? The electric field intensity. Now, I think the problem is asking us to find what is the potential, the difference in potential. In other words, the Greek letter phi. Now, what we should do? Let's go back again, do it step by step, and then we'll check to see if the calculations are correct. Right. So this was when small r was bigger than capital R. In other words, outside of the charge sphere. And this was the case when r is smaller, small r is smaller than r. Okay, let's make it a bit more clear. I was actually write it. So small r is smaller than capital R. In other words, it's inside the charge sphere. Now, if I want to find what is the potential, what do I need to do? Remember, the relationship between the potential and the electric field intensity is that the negative of the gradient of the potential is going to be equal to E. And again, both of them are vector fields. Now, this one can be written actually as delta phi is going to be the integral of phi times delta L. Yeah? So you can write it both ways, and that's perfectly fine. And again, keep in mind this delta L, in that particular case, we take it again in the direction which goes from the center of the sphere outwards. So it will be in the same direction as whatever is the direction of phi. So again, this dot product of two vectors is going to be just simply the algebraic product of those two quantities, the magnitudes of those two quantities. Let's see what happens. So we have here, we found that E was sigma R 3 epsilon 0, and this is now multiplied by dr. So we need to find what is the integral for that, yeah? Can someone help me with that? Can someone tell me what this expression will give me when I integrate it? I have sigma 3 epsilon 0, all those are constants that can come outside. So sigma 3 epsilon 0. What about r dr? It's going to be r squared over 2, yeah? Here, obviously, we have the limits of integration. And the limits of integration will be from what to what?
Thinking the radius.
in the solution of the problem, and again, we'll look again so we don't make any mistakes by not paying particular attention. So he's considered again two different areas, one outside and one inside. When he takes somehow the expression for the outside, it goes from whatever r is the value up to the infinity. And the assumption is that the potential of the infinity is equal to 0. Right, so if we look at this expression over here, right, we have phi of out, the potential when it's outside of the charged sphere is going to be the integral from small r to infinity, EdR. So again, imagine this is the sphere. It has the charge. This again surface that we put outside. So this is the small r. And again, we assume that the potential of infinity is equal to 0. So if you look this expression over here, the same thing we did before. So the E is given by this expression, yeah? Those are the things we calculated earlier. So if I have this expression over here, in other words, the integral from R to infinity, and then the density, times R to the cube power, etc., etc. By calculus, we know that this is going to give us this result. Is this clear? Also, I should do it separately. Please do not
Do it separately. Yeah.
do it separately, right? Okay. I'll do it here. So again, we keep in touch. So we assume if we look outside of the charge sphere, we assume that phi out at infinity is equal to 0. That's the way the assumption of the convention is. Yeah. So this one, from this known formula, which I said again, can be written also as delta phi equals integral of phi dl. So this is basically from the limits of integration is r to infinity, yeah?
Yeah.
Now, if you go back, we're able to find that this expression here is the value for E for outside the sphere. So it's basically rho or rho 0, which is the density, and then r cubed, where r is the radius of the thing, of the sphere, 3 epsilon 0, the permittivity of a free sphere, and then times r squared. Now, this by what we know about integration, the 1 over r squared, when we integrate it, will give us minus 1 over r, yeah? I mean, this is calculus. So this one is basically equal to rho 0 r cubed sigma 6 epsilon 0 times r. Yeah? Is this clear? Hopefully it is. Now, if we do the same thing for inside the sphere, and if we take, let's say, now we are now in this expression over here, same exact thing, same formula. So phi in at r, and then phi in at capital R, because now again, this is capital R, but we are inside. So we basically take the integral from this point, where it's R, to capital R. Yeah? Now, yeah, please go ahead. You want to say something?
No.
No. Right. Now we found E from previously, and E was equal to this expression here. Yeah. This was the E inside the sphere when small r is smaller than the capital R. So if we place this expression there, yeah, it comes directly from here. And we'll do the integration. it will give us rho 0 r to square sigma and 6 epsilon 0. And again, it goes from small r to capital R. And this gives us this expression. Yeah?
Yeah.
Now, but this was this. This was this. So from here, we can say that phi in at small r, where r basically is the variable, is going to be r0, r to the power of 3, 6 epsilon 0, minus rho 0, r square, 6 epsilon 0, plus phi in at capital R. Yeah?
Yeah.
Now, this is something we need somehow to incorporate in order to be able to find what must be this phi in at capital R. Phi in at capital R and phi out at capital R, because of the continuity of the potential, has to be exactly the same. It has to have the same value. In other words, those two expressions that we found for R less than, for small r less than capital R, and for small r bigger than capital R, they have to be equal to each other, right?
Yeah.
So if we equate those two expressions, we can find that actually phi in at R is given by this. Yeah? So for those two expressions to be compatible, in other words, to be exactly the same, when small r equals to capital R, then phi in at R has to be equal to this. And if that's the case, if we substitute for phi in this value here, we end up with this expression. And that's pretty much the end of the problem. Any questions on that?
None. None from me.
Okay, let me again, I think it's only one problem left, and we'll do it next time. In the meantime, let's do a few more things. My understanding is that you're going to have some extra hours in tutorials, possibly about vector calculus, so you get some very good, deep understanding what it's about. Now, if I have expression for a field, f equals, I don't know, xy I plus x squared y j, and someone tells me, how do I find what is this expression? I keep making the same exact thing. If I go from this point here, which is 0, 0, 0, to this point over here, which is 2, 0, 0. So I have this field, which is given by this. I mean, the expressions x, y, and the components, in other words, for the j and the I component can be anything. It can be exponentials, it can be anything you can imagine, because it's totally a theoretical problem. And I need somehow to figure out what is this line integral when you go from this point, in other words, the 0, 0, 0 point to the point 2, 0, 0. Here, in other words, x equals 2, y equals 0, and z equals 0. Can anybody tell me how we can do that? Right. I think in the first class, in the first meeting we had, we said that the dr is going to be equal to dx times I plus dy times j plus dz times k. When I move from the point 0, 0, 0 to the point 2, 0, 0, the only, let's say, difference that changes is only the dx. So when I have to find this expression over here from the 0, 0, 0 point to the t 0, 0 point, all I have to do basically is take this, the component of the I, which is xy, yeah, multiply by dx, and that and integrate that from 0 to 2. And this will give me the work done or the calculated in essence, because that's, if you want to put in physical terms, this expression over here tells me basically what is the work done when F is moving from the point 0, 0, 0 to the point 2, 0, 0. But again, the understanding of what is the meaning of the dot product boils down to this expression over here, which is in essence y x squared over 2, and if we substitute the values, practically will give us practically 0. And again, I took those things in random, so most probably don't make any sense. If I didn't have the y here, I can actually forget about the y here. So this gives me some value there, right? All I need to do is basically substitute for x, whatever is the value here, 2. So it's 4 over 2, which is 2. Does this make sense?
Yeah.
Yeah. So when someone tells you how you're going to calculate, let's say the work done from here to there, that's what you do. If someone tells you how you calculate now the work from along the line y equals x, you do the same exact thing. You come over here and you substitute whatever is x equals to y, and then you calculate the integral.
That's cool.
Yeah.
Okay.
I was here, for instance, and I do that. I'm going to have again. I wasn't very particularly careful choosing those expressions, but let's assume for sake of arguments, it is what it is. So I'm having integral of xy by x equals y. So this is basically x squared dx, and the other one again is x squared y. But again, y equals x. So again, same thing. So this is y to the power cube dy, and then just simplifying this integration, and then substitute what is the value that x and y change. Yeah. So if I say what is the work done from the point 0, 0, 0 to the point, I don't know, 3, 3, 0, you just simply substitute both over here from 0 to 3. Now, if someone asks you to prove that this field F, it is conservative field, what do you want to do? If someone asks you the question, if this is a conservative field, how are you going to respond to the answer?
Sorry. Yeah.
If this is easy to find, you do it this way. So you say, if the curl is equal to 0, remember curl was this expression. It is not always the easiest thing to do, but if it is easy, you calculate it the way we said a couple of times, and if you haven't learned it yet, we can still do it a couple more times until you learn it. So one way is basically to calculate this expression. If it's equal to 0, it means that it is conservative. That's the end of the story. The other possibility is that if someone tells you you go from here to there and from there to here, yeah? And then you return from here to there. So practically the work done by moving from this point to this point, and then to this point, and then from this point to that point. In other words, the line integral is a closed integral. And if the work done over there is equal to 0, it's an indication, a very strong indication that's a conservative field. Yeah?
Yeah.
Right. Any questions? Any questions? Let me say that again with regard to this nabla. The nabla, if it applies to a scalar, will give us a vector or a scalar. If I apply this nabla to a scalar field, will the result will be a vector or scalar? This is going to be again partial of f with respect to x, y, and z, which is a vector, yeah? If I apply the same exact thing to a vector field, this is going to be the f of x. In other words, the component of the vector field in the x direction plus the component of the vector field in the y direction, and then the partial derivative with respect to that direction, and the component of the vector field in the z direction. But this thing, the whole expression, it is scalar or vector?
Yeah.
Scalar, yeah?
Yeah.
So, yes, so when it applies the nabla to a scalar, it will give us a vector. When it applies, so this is the case, when it applies to a vector, they call this the gradient. And they call this the divergence. And as we said, there is the third application of this nabla operator, where they call it the curl.
Sorry, can you repeat the gradient? Like they call what the gradient?
Okay, I'll say it in a different way to understand what you're talking about. Can I erase that a couple of things so you have space to write? Or
Yeah, cool.
let me see if I can find some empty space somewhere. All right. Made a lot of mess. I write it here. Right. Let's assume we have a surface x, y, and z is equal to a constant. Yeah? Do we all understand that?
Yep.
This can actually look something like this in 3 dimensions. If I take the total derivative, d phi, obviously d of c is going to be equal to 0. Yeah? Because the derivative of a constant, we know it is 0. But what about the derivative of d phi? How can I write it? Can I write it this way? Partial of phi with respect to x dx, partial of phi with respect to y dy, plus partial of phi with respect to z dz. Can I write it this way? The answer is yes. Yeah? I don't know how much exposure you had to vector calculus, but that's again pretty much starts from there. It's one of those fundamental theorems of vector calculus. Now, this thing I can actually write it differently as well. I can write it partial of phi with respect to x times I, partial of phi with respect to y times j, plus partial of phi with respect to z times k, and then parenthesis dx times I plus dy times j plus dz times k. Yeah?
Yeah.
This expression over here, we call it the gradient. And this basically, it's basically dr. And dr is what they call the position vector. In other words, if I am, let's say, in 3-dimensional space and I want to be here, this here they call it r. So if I go in a point nearby, I call this r plus dr. So the difference between them, this is dr. Now the meaning of that, this being equal to 0, means that the gradient is in essence perpendicular to the dr, because dr is the distance between two very close located points. It means that the gradient is perpendicular to that surface. If I have, in other words, a surface that is given by this expression, phi of x, y, z equals to constant, and I go through this process, find the gradient, with this, let's say, manipulation, is proven that the gradient is perpendicular to that surface at that particular point.
Okay.
I know too many new things for you from vector calculus, and probably, I don't know what is your background vector calculus. I'm trying somehow to repeat things again and again. And hopefully at least, even if you don't understand them in depth, you can understand them mechanically and you can use them. And please do not hesitate. If something is too obfuscated, please ask me to explain more and more. I don't mind explaining the same thing again and again. Because many times I might assume certain things are obvious or supposed to be known, but maybe not. Right. So is it clear about the gradient?
Thank you.
Now, for those of you who might later on in your life, your academic career or professional career, decide somehow to deal with optimization or any of those fields, the gradient, and again, maybe some of you heard about the words machine learning, etc. Those concepts are quite useful. They're quite expedient in using along again concepts such as optimization, machine learning, and the likes. But obviously, again, it requires a lot of dedication, a lot of effort, and to learn those things, they're becoming working knowledge. And I apologize that we go through those things rather fast, and then sometimes we just go from one point to another without necessarily giving all the necessary background, but under the circumstances, we try to do whatever is possible. Any questions, please? If you don't have any questions, I don't know about you, but I'm tired. So let's call it for the day today, right?
Yeah.
If you don't have any questions, I don't want somehow to stay more. And you deserve somehow to go and get some rest. I will talk to you on Thursday at 5 o'clock. My understanding is you're going to have another 2 tutorials tomorrow and Friday. Not with me though, with Professor Bai.
Okay.
The same one who gave you the lecture, I think was last week. Yeah. Right, okay. So have a good night.
Thanks. Good night.